Hello everyone. Today we'll be discussing about a very interesting topic which is called Newton's ring experiment or just Newton's ring setup. So we'll be understanding what this setup is and then we will go for the derivation. Now Newton's ring experiment is basically we have an assembly of plano-convex lens. You can see in the diagram on the right hand side. Plano-convex lens is placed on a plain glass plate and a monochromatic light from source S made parallel with a lens and falls on a glass plate which is inclined at 45 degrees. Now please see here, Newton's ring experiment is a special case of a wedge-shaped film. Why do I say so? Because you see here, where is the wedge formed? This is an air wedge here in the diagram where I have drawn an angle theta. Now this is the sides of the plano-convex lens which make a air wedge. So here the case of a normal incidence, because the light gets reflected from the 45-degree glass plate and falls onto the plano-convex lens, and then again the light gets refracted inside the convex lens, then again bounces back from the glass plate, and you have an interference pattern of the light coming out, and using a microscope we get the reflected interference pattern, and you can observe the interference pattern here. But what is happening? So we have interference between the upper part of the wedge and lower part of the wedge. Between these two waves we get the interference. So that is how, as the thickness of the air wedge changes, you get the maxima minima patterns. And similarly you see here just below the diagram, this is the pattern in the Newton's ring experiment. So you see the thickness of the fringes keeps changing. Okay, thickness of the fringes keeps changing, or I should say the diameter of the fringes keeps changing, and the center of the pattern or the zeroth order pattern is dark because of the pi phase change during reflection at the glass plate at this point O. So we'll start with the uh, explanation of this, and we will continue finding, because it is a special case of wedge shaped film, we will not be deriving anything here. We will be importing the results from the wedge shaped film, but we will have to derive the expressions for the diameter of the rings, the dark and bright rings, and we will have to see the applications of Newton's rings. So we consider, in wedge-shaped film case, we had the condition of maxima to be 2 mu t cos of r plus theta equal to 2n minus 1 lambda by 2. For minima, we had 2 mu t cos of r plus theta equal to n lambda. Now, as I said, it is a special case. Newton's ring setup is a special case for wedge-shaped film. Why it is a special case? Because here we have a normal incidence. So we say I and r equal to 0 degrees and theta also approaches 0 degrees. So we can safely put these three to be 0. And so we have the new conditions for maxima and minima for Newton's ring case. We have the maxima condition to be 2 mu t equal to 2n minus 1 times lambda by 2, and 2 mu t equal to n lambda, which is the minima condition. Now, as the rings are formed away from the center, so the thickness of the film also changes. So it is safe to assume that this T can be called as Tn for nth fringe. So let me continue further. We would now find out what is the diameter of the rings. That is very important because it will be used in the applications of Newton's ring. So to find the diameter of the ring, what we do is we extend the geometry of plano-convex lens, where capital R is the radius of curvature of the plano-convex lens. That is BOL here, if I have to say. T is the thickness of the air film at point L. Rn is the radius of nth ring corresponding to the air thickness T, or as I said earlier, you can call it as Tn because it corresponds to some nth ring with radius Rn. Now we will use a simple result of chord theorem which says that Am times Mo is equal to Bm times Ml. So in this case, AM is this length and this is MO, and BM and ML are these, which are nothing but Rn each. Now what is AM? This entire distance AO is nothing to R, it is 2R. So we have AM to be equal to 2R minus Tn, rightly written here. So you have, we substitute the values for AM, MO, BM and ML. We get 2R minus Tn times Tn is equal to Rn square, or we have Rn square equal to 2R Tn minus Tn square. But please remember, because theta almost approaches 0, so this area is very flat. Okay, so it is very safe to say that Tn is far less than R, radius of curvature. So if Tn is far less than R, then I can safely assume Tn square to be 0 as compared to 2R and 2RTn. So I have, if I remove this one Tn square, I have Tn equal to Rn square by 2R, or Dn square by 8R, where D is the diameter of the ring. See here, see the diagram. Now once I know the relation between diameter and the thickness of the ring, I will just substitute back in the maxima and minima conditions to get the diameter of the rings. So here I use the maxima condition because I'm talking about dark ring diameter. So I have this formula. Here I substitute Tn is equal to Dn square by 8R. I get diameter is equal to root of 2 times 2n minus 1 lambda r by mu, which also tells me that Dn is proportional to the square root of odd natural numbers. Similarly, I find the dark ring diameter using the minima condition. 2 mu Tn is equal to n lambda. So Tn has to be substituted again. I get Dn is equal to root of 4n lambda r by mu. Here diameter Dn is proportional to the square root of natural numbers. But why these diameters I'm calculating? Because for the applications of Newton's ring, here we set up the Newton's ring experiment to find the unknown wavelength lambda, wavelength of the source of light, and measurement of the unknown refractive index mu. Where is this refractive index coming into picture? This mu was the refractive index of, I'll go back to the diagram, this area where there was air. Now just imagine I put a drop of an oil. So I can find, once I set up the experiment, I can find what is the refractive index of the liquid used. So what we do is, we set up the Newton's ring experiment and we obtain any two diameter of the rings, any two diameters. Say I have a 20th ring and I have a 15th ring. So I denote the 15th ring to Dn and 20th ring to Dn plus P. So what will be P value? That will be 20 minus 15. So that will be 5. So P is just a counter for the next ring. So let Dn and Dn plus P be diameters of any two Newton's ring. Then using the formula for diameter of dark rings, I have this formula, Dn square equal to 4n lambda r. And similarly, the same formula I extend for n plus pth ring also. So this becomes 4n plus p lambda r. In this case, because I'm bothered about finding the unknown lambda, so I will keep mu equal to 1. I will use air. So I subtract these two, dn plus p whole square minus dn square, I get 4p lambda r, or the lambda is dn plus p whole square minus dn square by 4pr. So it is very simple to obtain unknown wavelength. Now, what if I have a refractive index mu for the liquid? So again, I will use the same formula, but in this case now mu is not equal to 1 because we have placed some liquid. It is not equal to 1. So the same formula holds good, and doing the same thing, we get again the refractive index of the unknown liquid to be dn plus p whole square minus dn in air, dn square I meant, divided by dn plus p whole square minus dn square in liquid. So what we have done now is we set up the experiment in air and find the diameters of the two rings, and again we next time we put a liquid drop and do the experiment again, and we find the same nth and n plus pth rings diameters. They will have shifted by now, and that shift will be corresponding to the refractive index. So once we have these four rings diameters, we can easily calculate the unknown liquid refractive index. So that is all about Newton's rings. Thank you.